5, 4, 3, 2, 1, 0, +1, +2, +3.
PSLV XL will inject Chandrayan-1 into an elliptical transfer orbit ETO. ETO measuring 250 kilometers perigee and 22,000 kilometers apogee. PSLV will inject the Chandrayan into this orbit at a velocity of 9.89 kilometers per second. From here on, all the post-launch operations will be coordinated by ISRO Telemetry, Tracking and Command Network, ISTRAC, Bangalore. The existing network of ISTRAC ground stations, along with support from foreign agencies, will track and communicate with Chandrayan-1 during its journey towards the Moon. The orbital period of the spacecraft in ETO-1 is 6.5 hours. The spacecraft circles the Earth for 3 to 4 times in the same orbit. The LAM is fired near perigee, which increases the apogee to 40,000 kilometers and enables Chandrayan-1 to go into the second extended transfer orbit, ETO-2. The orbital period of the spacecraft increases to 18 hours. After the second LAM firing, Chandrayan-1 will go to the third extended transfer orbit, ETO-3, increasing the apogee to 70,000 kilometers. The orbital period will be 24 hours. Chandrayan-1 will be put into an elliptical orbit where the apogee will match with the distance of Moon from Earth. Satellite will take 11 days to complete one revolution in this orbit. During subsequent revolution, the trajectory correction for approach to Moon will be carried out. Beyond the 100,000 kilometers, the ground stations of the Deep Space Network will provide support to the mission. From here, the spacecraft will coast along for about 5.5 days before it reaches the vicinity of the Moon. The newly established Indian Deep Space Network, having 18 and 32 meter antennae at Bailalu, near Bangalore, is a very unique facility, having several critical technologies established for the first time in the country. The 32-meter antenna and the associated electronic equipment has been designed and developed for ISRO by Electronic Corporation of India Limited, ECIL. ISRO Satellite Center supplied the feed subsystem. On-site installation and commissioning are executed by ISRO Telemetry and Tracking Command Center, ISTRAC. Operating in S and X bands, the 32-meter antenna is capable of receiving extremely weak signals from the spacecraft, which are millions of kilometers away from Earth in deep space, and can also send very strong signals to the spacecraft. An 18-meter diameter antenna working in S and X bands will also support the mission. The Indian Deep Space Network antennae can be operated remotely from ISTRAC Network Control Center at Bangalore through a monitoring and control system. As Chandrayan-1 spacecraft travels into deep space, mid-course corrections will be carried out as and when required. When the spacecraft is about 500 kilometers from the lunar surface, a major maneuver called Lunar Orbit Insertion, LOI, is performed. Chandrayan-1 will achieve its final moon orbit 20 days after the launch. After this, Chandrayan 1 will enter into an elliptical orbit around the Moon, with the nearest point being about 500 kilometers from the lunar surface and farthest point being about 5,000 kilometers. After the subsequent health checks, the spacecraft's orbital height is planned to be lowered through a series of planned maneuvers to achieve the target altitude of 100-kilometer circular polar orbit over the surface of the Moon.
After reaching operational polar orbit, the payloads will be commissioned one by one. The first to be commissioned is the Moon Impact Probe, MIP, a technology demonstrator. It will be released at the earliest opportunity once operational orbit has been reached.
After its release from the spacecraft, the retro rocket of MIP will be fired and it will slowly start its descent to the lunar surface. During the descent, MIP's video imaging system will acquire images of the surface of the Moon. The mass spectrometer will measure the constituents of thin lunar atmosphere, and the radar altimeter will provide instantaneous altitude and hence give inputs for future Indian soft landing missions. Thereafter, MIP will impact on an identified area in the south polar region of Moon.
The payloads on Chandrayan 1 are engineered to acquire scientific information on the Moon through remote sensing in the visible, near-infrared, microwave, low and high-energy X-ray regions of the electromagnetic spectrum. The cellular-logical mapping will identify different features on the surface of the Moon and will help us understand the different layers of the Moon's crust. TMC and LLRI will carry out topographic mapping of the lunar surface.
TMC will take three-dimensional black and white imagery of the lunar surface with a resolution of about 5 meters. LLRI will provide accurate altitude or height information of the spacecraft above the lunar surface for topography and gravity mapping.
The chemical mapping of the lunar surface will help us in understanding the formation and evolution of the Moon, as well as in finding out the possibility of lunar mining for precious elements. 6 and HEX will carry this out.
6 will measure fluorescent X-rays coming from the Moon from lighter elements like magnesium, aluminium, silicon, calcium, and iron. On the other hand, HEX will map the heavier radioactive elements like uranium, thorium, and lead.
High-resolution maps revealing mineral composition will help us in understanding the early evolution of the Moon, provide information on lunar resources, and support the planning of future missions. HiSci, SIR-2, and M3 will provide these maps.
HiSci will rely on the visible and near-infrared rays reflected from the Moon and will slice the incoming light into 64 parts to observe many specific details. SIR-2 will help to analyze lunar surface and to study the vertical distribution of lunar crustal material. Besides, it investigates the process of basin, maria, and crater formation on the Moon, and it will survey Moon's mineral resources. Similarly, M3 will explore lunar mineral composition in the context of Moon's evolution.
Radon will measure the nature and composition of the radiation in the vicinity of the Moon. This data will help us in assessing the radiation shielding requirements for future human missions.
Radon will qualitatively and quantitatively measure the particle flux, deposited energy spectrum, accumulated absorbed dose rates in lunar orbit.
SARA will be the first ever energetic neutral atom imaging mass spectrometer to be used for planetary